So today we'll discuss scheduling for multiprocessors and real-time systems. And let's discuss for multiprocessor scheduling. So we have a look at different granularity of parallelism and synchronization. And let's look at each individual grain size a little bit detailed. The first one is called independent parallelism, which means each process or thread is independent. There is no need for synchronization, there is no dependency. So each task represents a separate independent application or job. And typically in a time-sharing system, in a multi-user environment, each task is usually independent. And each user is performing a particular application. So in this case, multiprocessor environment can provide good service and performance for these types of parallelism. And because we have more than one processors, the response time can be reduced because they can be serviced by different processor or different core. And nowadays, as I have mentioned in the previous lecture, we have multi-threaded processors in today's commercial processors. So Core i7, maybe 4 quad-core or 6-core, and each core is multi-threaded, and it's called simultaneous multi-threading. It's been proposed by the PhD student from academia at University of Washington. He is now a faculty professor at UC San Diego. And it actually exploits this independent parallelism. So if you have a pipeline with wide issue superscalar processor, which means, as I mentioned, you can execute multiple instructions at a time every cycle. But because of dependence, sometimes you cannot execute, even though it's code issue or 6 issue, you can only execute 1 or 2 instructions because of dependence. But if you have 2 program counters, if you fetch 2 instruction streams together, if you share the same instruction and pipeline, then you can increase the pipeline utilization, and you can increase the instruction per cycle, which is how many instructions every cycle you can complete. So in that way, you can improve the performance, not single program performance, but the throughput, because you can execute instruction from 2 different instruction streams. And it's called simultaneous multithreading, and it's utilizing this independent parallelism. So today's multi-threaded processor hardware actually exploit this independent parallelism. It's easy to exploit because you don't have to coordinate threads because there is no dependence. Question?
No.
Okay. And multiprocessor environment is also they can utilize this independent parallelism because you can assign any task to any other core or processor. Coarse and very coarse grain parallelism. So there is not much dependency and not much coordination, but from time to time there need to be some coordination, and it's called coarse grain or very coarse grained parallelism. And this is typically useful for multi-programmed uniprocessor, and if you are learning concurrent process means you are not learning in parallel, you are interleaving process by doing context switching, because there are some coordination. Sometimes even if you are running on a uniprocessor, because this granularity is quite big, you can exploit some amount of parallelism in this uniprocessor environment. And also, in this case, you can run this kind of application on multiprocessor with little or no change to user software. So traditionally, concurrent process that are cooperating at a coarse grain level can be run on a multi-programmed uniprocessor, and also can run on a multiprocessor environment with no modification. Okay. Medium-grained parallelism. So actually, a single application can be implemented as a collection of process or a collection of threads. In this case, programmer must specify the potential parallelism of an application, and because of this granularity is smaller, you need a high degree of coordination and interaction and dependency among the threads. And this is called medium-grained parallelism. Because various threads of an application interact so frequently, scheduling decision on one thread may affect the performance of an entire application. So to improve the application performance, all the threads should perform well. If some thread is not performing well, then it will affect the entire application because there are dependence and coordination. Some other thread has to wait until that thread, the performing low, has complete. Okay. Fine-grained parallelism is, as you have discussed, less than 20 instructions. There are coordination, so this is hard to exploit because there are too much coordination and synchronization and dependencies. Usually this can be exploited at instruction level from the hardware. For the operating level or scheduling level, it's not easy to exploit. And it represents a much more complex use of parallelism than is found in the use of thread. So thread is a little bigger, right? So fine grain, the grain size is smaller. So it's a specialized and fragmented area with many different approaches, but it's hard to exploit area. Okay. So in a multiprocessor, we are trying to exploit these different levels or different granularity of parallelism. The easiest we can get is the independent parallelism, and then coarse grain, and then medium grain, and so fine grain. It will be almost impossible to exploit in a multiprocessor environment. Scheduling on a multiprocessor involves three issues: how to assign process to processors, and whether we will allow multi-programming on individual processors. So in a uniprocessor, to increase CPU utilization, we allow multi-programming or multitasking, which means every time there is a I/O block, then we context switch and we run another process to increase CPU utilization. Because instead of idling CPU, it's better to run other applications. But it may not be true in multiprocessors, because sometimes there are many cores, many processors are available. So the goal is to achieve a good performance on application, not just achieving high CPU utilization. If you want to achieve high CPU utilization, sometimes we have to sacrifice application performance, even though we can improve throughput. So we'll look at some examples. So that's another issue, whether we'll allow multi-programming or multitasking on individual core or individual processor. And the third issue is the actual selection of process to run. So after we assigned, there are multiple ready process, which one we'll choose. And we have looked at different scheduling algorithms. We sometimes use priority, or we use path to usage, such as feedback scheduling. If some process is using CPU for a long time, then it will move to the lower priority queue to give more favor to I/O bound jobs, right? But this kind of priority or path to usage may improve performance for uniprocessor, but this kind of complex scheduling may not be as effective as in uniprocessor for multiprocessor environment. And sometimes this complexity may be unnecessary or even counterproductive for multiprocessors. You don't need that kind of complex scheduling because there is not much difference. We look at some examples. Okay? So the approach taken will depend on the degree of granularity of application, how much parallelism the application have, and the number of processors available. If we have many processors, the goal might not be processor utilization. The goal might be application performance. Then we may consider some different type of scheduling. So let's look at each issue. The first issue is this assignment of process to processors. So as I said, this is still ongoing research area. Multiprocessor scheduling or real-time scheduling is an active area of research in computer science. So it's somewhat advanced topic for undergraduate students. So we'll just review how it's different and what approach are taken for each issue. So how to assign process to processors. Assuming all processors are equal, if you assume uniform multi-core environment, it is simplest to treat processors as a pooled resource and assign process to processors on demand, because each processor is about the same, right? Equal. We can assign this process to any of these processors, and we can consider two different options. One is static assignment, the other is dynamic. Static assignment is a process is permanently assigned to one processor from activation until its completion. So this means we have a dedicated queue for each processor. Okay, so after we assign process to one processor, it remains there until its completion. Okay, this is called static assignment. So advantage is scheduling is overhead is small, because after we assign, we don't have to do any other scheduling. Disadvantage, sometimes one processor can be idle with an empty queue, while another processor has a backlog. Backlog means there is a queue waiting. Many processes are waiting, because after assignment, it cannot move to another queue, right? It should be dedicated to that processor. So this is quite simple, but the disadvantage is in terms of load balancing, it may not be good. So to prevent this situation, we can use a common queue or shared queue. So there is a one queue and many processors, and so because there is a single queue, we can assign. We take the first ready process and we can assign to any of these processors. But after I/O block, it go back to the queue, and next time it can be assigned to different processor, right? So if you do that, then during the lifetime of this process may be executed on different processors on different times, right? So this is not a little different from static, right? Static means it's dedicated, but this is not dedicated anymore. You are on the stack tab. 졸립지? Okay. So another option is doing dynamic load balancing. So threads can be moved from one queue for one processor to another queue for another processor. So you can actually move thread or process from one queue to the other using dynamic assignment, and Linux actually uses this kind of approach for multiprocess scheduling. Okay. For this process assignment, we can use we can assume two different architecture. Okay.
In regard to queues, when moving processes between different queues.
This one?
Yes.
Okay.
Does that involve processing from the processor to move, like to arrange the queues? Where is the?
I guess because of load balancing, maybe you want to balance the load. Okay, so if you want to prevent idle processors, so you assign first. Maybe you can assign round robin style. assigning to each different processor. But some processor, the queue might be idle, then maybe you can take a process waiting in the queue,
Yeah.
and you can move to the other queue that's idle. Right? That's possible. So that you can balance the load.
Yeah, but when you move from one queue to another,
Okay.
what's in the computer is it the processor that's involved with
Operating system, scheduling.
Yeah.
Right. So it's ready in the queue means you change the status. So you take the process out of the queue from that processor,
Yeah.
and then you move. There should be multiple queues for each processor, right, in the operating system,
Yeah.
in the data structures. So you take away from one thread from this queue because there are some idle queues, and move it to another idle queue.
So the kernel is the
That's right, operating system kernel. The
Yeah.
process is not moving.
no exactly. I understand.
Right.
Yeah. But it's
Okay.
The last sentence on the static assignment.
Okay.
If the process comes back to different processor, then it is not a static assignment. Which means static assignment should be on one processor and end at that point.
Right. I think if you use a shared queue, whenever you have a I/O block, then you go back to the queue, and it can be assigned to any other processor, right? So in that case, I don't think it's static assignment. Okay. If it's running to completion to each processor, if it's dedicated, then maybe it can be static. Okay.
In static assignment, it talks about processes, but in dynamic load, it talks about threads.
So actually, in the textbook, it's actually changing thread and process
So it
interchange. It doesn't matter. You can move process or you can move thread. Okay. Okay. In terms of this processor and process assignment, we can assume two different architecture. One is master-slave architecture, the other is pure architecture. In a master-slave architecture, so we can differentiate a master processor with slave processors. So there is a master processor which can run key kernel functions, and it's responsible for scheduling. So scheduling is done only in master processor, and it has control for all the memory and I/O resources. So maybe all the kernel, including scheduling functions, are done by the master processor. So the advantage of using this kind of master-slave architecture is it's quite simple and requires little enhancement to a uniprocessor multi-programming operating system, because there is only one scheduler running in master processor. So it's similar to uniprocessor environment. Otherwise, pure architecture, each processor can run its own scheduler. So you have to coordinate different scheduler, and you have to coordinate resource conflicts and so on. But in a master-slave environment, there is only one processor responsible for scheduling and all the other kernel functions. So for the slave processors, they run only the user code. And whenever they have I/O or they need operating system service, they request master for this service. Okay, so the advantage is quite simple, and you can use uniprocessor scheduling with little modification. And the disadvantage of this approach is if master fails, then it can fail the entire system because it's vulnerable. And master also can become a performance bottleneck because all the kernel requests can go to master processor. So the other architecture is pure architecture, which means kernel can run on any processor. And scheduler, each processor has its own scheduler. So each processor does self-scheduling from pool of available process, and this complicates the operating system because operating system must ensure that two processors do not choose the same process, there should be some coordination difference among the different schedulers, and you need to reserve and synchronize competing claims to resource from different schedulers. So this is more natural way of doing multiprocess scheduling, but it's more complex. So to simplify, you can use this master-slave architecture, but there are some limitations. Right? So eventually this might be better. It's more distributed, but it's more complex. Okay. Okay, so that's the assignment of process to processors. The second issue is whether we should allow multiprogramming on each processor or each core. In uniprocessor, of course, we have to allow multiprogramming or multitasking to utilize CPU more. We don't want to idle CPU because there is only one CPU. Let's look at multiprocessor situation. When each process is statically assigned to a processor for the duration of lifetime, okay, for the static assignment, should we allow multiprogramming on this processor? That's the issue. Okay. In the traditional multiprocessor with coarse-grained or independent synchronization granularity, it is clear that each individual processor should be able to switch among a number of processes to achieve high utilization. So for coarse-grained or independent parallelism, maybe it's better to allow multitasking or multiprogramming to utilize CPU more. But for medium-grained application running on multiprocessor with many cores or many processors, this situation is not clear. Yeah. With many processors available, it's no longer paramount. Paramount means it's no longer best that every single processor busy as much as possible. So the focus might not be just CPU utilization if you have many available processors or many available cores. Rather than, we may be concerned to provide best performance for the application. Okay? An application can consist of many threads, and if you allow multiprogramming, it may run poorly, because multitasking while multiprogramming means whenever it's blocked, you switch to another thread, and then there might be another thread waiting in other processor, right? They might be blocked because of frequent coordination or synchronization. Then maybe if one thread might suffer from the performance because of multitasking, it might affect the entire application performance. Okay. So in this case, an application that consists of many threads may run poorly unless all of its threads are available to run simultaneously. To get the best performance for application, it's better to run these threads in parallel in different processor core at the same time. If some thread is blocked and is context switched by another thread because of multitasking, even though other can run, this might affect the entire application performance. Okay, so in a multiprocessor with many cores, this processor utilization might not be the goal, rather than the entire application performance might be more important. That's what this slide is trying to explain. Okay, so the focus might be the entire application performance, not just CPU utilization as in uniprocessor. And also it depends on the parallelism granularity. If the granularity is coarse or independent, it's okay because there is not much coordination. You can use multitasking. But if there are too many coordination, such as medium-grained application, then it's better to allow them to run simultaneously, which means we may not allow multitasking. Okay? Okay, so let's discuss other issues. Process scheduling. So in a multiprocessor environment, usually processes are not dedicated to processors. Instead, a single queue is used for all processors. a shared queue. If some sort of priority scheme is used, then there can be multiple queues based on the priority. In this case, we can view the system as a multi-server queuing architecture. Okay. This shows how scheduling algorithm affects the throughput for uniprocessor and dual processor environment, how it's different. Okay. So here we are looking at this curve. This is the first curve showing the x-axis is called coefficient of variation, which is called CS, which measures the coefficient of variation. CS is calculated as of delta divided by TS, where delta is standard deviation of the service time and TS is the mean service time. Okay, so compared to mean service time, how much standard deviation it has. And if you have CS of 5, then standard deviation is about 5 times bigger, which is there are lots of variation in the service time. So CS equal 0 means sorry, CS equal 0 means there is no variation, standard deviation, which means 0. It's all service times are equal. So CS equal 0 corresponds to the case where the service times of all processes are equal. The larger the CS, the more variation in the service time. Values of CS of 5 or more are not unusual, which means there can be lots of service time variation in actual systems. So in a uniprocessor environment, if you apply, this is round robin to first come first serve throughput ratio. So round robin throughput divided by first from FIFO throughput. Okay, the ratio. So round robin should give better CPU utilization. Right? So in uniprocessor, the difference as the variation becomes bigger and bigger, the throughput of round robin algorithm is better. Right? But actually in dual processors, the performance difference between these two different algorithms is only less than 4%. So it doesn't matter much. It doesn't matter much. You don't have to use complex scheduling algorithm because there is not much difference, because there are more cores available. Either you use first come first serve or round robin, because whenever you can exploit more number of cores or more number of processors, the scheduling algorithm doesn't affect that much, because you can assign to different processor core. Okay? So if you increase number of processor core, I think the difference will be reduced. If you use more complex scheduling, there are some overhead. And also round robin, there is context switching overhead. So the difference between these two algorithms might be negligible or sometimes counter intuitive. Right? In multi-processor or multi-core environment. The similar situation can be seen in comparing SRT versus first come first serve. Okay. So in this graph, it's comparing shortest remaining time versus first come first serve. So shortest remaining time should give much better performance, right? Because it's more complex. So it can, in uniprocessor environment, as the variation becomes bigger and bigger, it can give about more than 20% throughput increase compared to FIFO scheduling. But in dual core, it's only about, I guess, about 6%, something like that, right? The difference between different scheduling algorithm will be reduced, and as you increase the more core, it will be reduced further. Okay, so the specific scheduling discipline or algorithm is much less important with dual processor than with uniprocessor. Okay, so uniprocessor maybe it's better. Sometimes you don't have to use complex scheduling algorithm. It's better to use straightforward, simple algorithm, which might be more effective. Okay, that's what this graph is showing. Okay, let's look at this issue, thread scheduling issue. On a uniprocessor, threads are used as a program structuring tool and also to overlap I/O with processing, right? But in a multiprocessor system, threads can be used to exploit true parallelism. And if you are careful, if you are doing some good job, dramatic performance gains are possible in the system with multi-threading, thread scheduling. For an application that requires significant interaction among threads, small difference in thread management and scheduling can have a substantial performance impact. So thread scheduling is more important in multiprocessor than in uniprocessor. And these are thread scheduling approaches, and we look at one by one. The first one is called load sharing. Load sharing. Load sharing means processes are not assigned to a particular processor. A global queue of ready thread is maintained. So it's like a shared queue. Okay? And each processor, when it's idle, it can select a thread from the queue. Okay? So this is called load sharing. We have a global queue, global shared queue, and each processor, whenever it's idle, it can select a thread from the queue. This is called load sharing. And gang scheduling is we schedule a set of related threads to run on a set of processors at the same time. This is called gang scheduling. So we select a group of threads that are related and assign this set of threads to a set of processors at the same time. Okay, instead of one by one, we do the group scheduling, and this is called gang scheduling. Gang scheduling. This is another approach. The third approach is called dedicated processor assignment. This is inverse opposite of this load sharing. We dedicate a group of processors to an application for the duration of application. So load sharing means it's like a shared queue. You can thread can run on different processor during the lifetime of the thread, but here it's dedicated to a particular processor. So you dedicate a group of processor to an application for the duration of the application. When this application is scheduled, each of these threads is assigned to a processor that remains dedicated to that thread until completion. Okay, the opposite case. And dynamic scheduling means during the course of execution, the number of threads in a process can be altered. If the software or environment allows this kind of number of threads change, then we can use this kind of dynamic scheduling. So these are 4 different approaches. Let's look at load sharing. Load sharing is the simplest approach. It carries mostly directly from a uniprocessor environment, and load is distributed evenly across the processor because there is a shared queue. Right? Okay. So no centralized scheduler is required. When a processor is available, the scheduler can run on that processor to select the next thread. And the global queue can be organized and accessed using any of the scheduling algorithms discussed in Chapter 9. So these are the different versions of load sharing. Even though we have shared global queue with many cores, many processors, we can use FIFO. When a job arrives, its threads are placed at the end of this queue. An idle processor selects the next ready thread, which it executes until its completion or blocking. Okay, if it's blocking, they go back to the queue, and then whenever it's idle, it selects the first ready thread. Okay. The other version is called smallest number of threads first. So the shared ready queue is organized as a priority queue with highest priority given to threads from jobs with smallest number of threads. If the job has small thread, then it gives higher priority. Okay, and this is non-preemptive version, and this is preemptive version, and these are different flavors of this load sharing. Okay. The disadvantage is central queue occupies a region of memory that must be accessed in a manner that enforced mutual exclusion. Okay, because there is only a single shared queue, and this can become bottleneck. And preemptive threads are unlikely to resume execution on the same processor. So if you use load sharing, whenever it's blocked, it can go back to the queue and it can be assigned to two different processors, which means the thread context thread caching in the previous processor cannot be utilized, okay, because it can be assigned to two different processors. So caching becomes less efficient than other case because it can be assigned to two different processors, okay. And if all threads are treated as a common pool of threads, it's unlikely that all of the threads of a program will gain access to processors at the same time. So it may seriously compromise performance. What this means. So this sentence means if you use this shared queue, global queue, then all threads are actually treated as a common pool of threads, right? So if you have many threads from a single application, and if you're lucky, each of the threads can be assigned to different processors, can run in parallel, but it's not guaranteed. So sometimes maybe two or more threads coming from the same application can run the same processor, which means there should be some coordination, which means it may compromise performance, because the best situation is if it's from the same application, you have to run it in parallel so that you can complete fast. Right? Otherwise, there are some dependencies and synchronization if they are assigned to the same processor. Okay, that's what this sentence is trying to say. But despite its disadvantage, it's one of the most commonly used schemes because it's simple. Okay, GAN scheduling, the second option. So it's assigning a group of threads to a group of processors at the same time instead of one by one. Okay, it's called GAN scheduling. The advantage is if closely related threads execute in parallel, synchronization blocking can be reduced and there will be less thread switching and performance can be increased. Okay, because the GAN scheduling is trying to schedule a group of related threads in parallel at the same time to a group of processors. Okay, and because they assign, maybe you can assign each thread to different processors and they can run in parallel, okay? Because they assign at the same time. So that means if they can run in parallel, synchronization will be reduced and there will be no thread switching, and eventually the performance will be increased because you can run all of these threads from the same application in parallel. Okay, and the other advantage is scheduling overhead may be reduced because single scheduling decision can affect a number of processors and number of threads at the same time. Okay, so instead of one by one scheduling, you can do group scheduling of group of threads and to a group of processors. Okay, that's the advantage. And this is quite useful for medium-grained to fine-grained parallel application whose performance can severely degrade when any part of the application is not running while other parts are ready to run. So for medium-grained or fine-grained parallelism, there are lots of coordination and synchronization and dependence. If you run them in parallel, then you can get some performance. Otherwise, it's hard to achieve performance because of too much coordination. And in this case, GAN scheduling can be quite effective. And it's also beneficial for any parallel application. Okay, that's called GAN scheduling. Okay, so I'm just giving you introductory, explanation. So this is still an ongoing research area. Okay, so we are just looking at how it's different, because nowadays multi-cores are common in actual systems, right? Even for smartphones, we are using multi-core. This is actual scheduling we deal with if you are going to industry or if you are going to academia in the future, okay? Because right now we have quad cores or 6 cores, but in the future, when we will work in the future, we will have many core systems. Maybe 16 cores or 32 cores are possible on a single chip, okay? So we have to consider this kind of issues. This is an example showing GAN scheduling of 2 different approach. So here you have 2 groups. The group means maybe application. In this group, it has 4 threads. This group has only a single thread. And you can assign CPU time, help and help. This is called uniform division. In this case, group 1 is utilizing these 4 processor cores, all of them, because you have 4 threads. They have 4 threads, but group 2 has only 1 thread. So this much is idle, right? So the idle time is about 37.5% of the entire CPU utilization. Okay. 전에 스택탑 여기 졸립지? But if you use instead of uniform division, you can apply division by weight, which means if this has 4 threads, this has only 1 thread, there are 5 threads. So you assign 80% of CPU to group 1 and 20% of CPU to group 2 because 4:1 ratio. Okay? And in this case, you can reduce this idle time of CPU to only 15% compared to uniform division. So for GAN scheduling, if you want to utilize CPU more, you can use this kind of division by weight. But this
won't you reduce the performance for application 2 as well, because it only receives 1/5 processing time?
That's right.
But that's
But you can increase CPU utilization. That's
the main goal.
If you want.
Yeah.
If you want. If you want. Yeah, different approaches. Okay. So this is still it's from the research paper in 1990. Okay. Let's look at the third approach, which is called dedicated processor assignment. So this is opposite of load sharing. So when an application is scheduled, each of its threads is assigned to a processor that remains dedicated to that thread until the application runs to completion. Okay? You dedicate thread to a particular processor. If a thread of an application is blocked waiting for I/O or for synchronization, then that processor remains idle. So in dedicated process assignment, there is no multitasking or multi-programming. You dedicate, but you don't context switch. You wait there. Okay? And this strategy might be effective for multiprocessor defense of this threat. In a highly parallel system with tens or hundreds of processors, processor utilization might not be no longer so important as a metric for effectiveness or performance. The total avoidance of process switching during the lifetime of a program should result in substantial speed up of that program. So you dedicate to a particular processor and you don't allow multitasking, which might sacrifice CPU utilization, but overall you can avoid process switching or thread switching, which might increase the speed up of that application because you can run in parallel, right, with dedicated assignment, and also you don't allow multitasking. In that way you can achieve the speed of the application instead of CPU utilization. Okay, that's the third approach. This graph shows application speed up as a function of number of threads. So this is another from the research paper. They are trying to learn two applications. One is matrix multiplication, and the other is FFT, fast Fourier transform. And they can change the number of threads from 0 to 24. So they increase this number of threads per application. And in this system, there is only 16 processors in this system. So in a multiprocessor environment with 16 processors, by increasing the number of threads, how the performance varies in terms of function of this number of threads. So this is speed up compared to no thread. Okay, and this is by increasing maybe 2, 3, 4, 8, 12, 16, 20, 24, and the peak speed up can be achieved at threads of 8, which means 8 threads for matrix multiplication, 8 threads for FFT. So because each thread can be assigned to different processor core. But beyond that, actually the performance degrade, right? Because if you have more threads, you have more thread switching and thread preemption that can actually increase overhead. And because you have only 16 processors, beyond the number of threads, if the number of threads are beyond that number, then you need to do some switching, right? Which increase actually overhead. So the performance worsens considerably when the number of threads in each application exceeds 8. So total exceeds 16 processors. And the total number of threads exceeds the number of processors. So the number of threads should be about as equal as number of processors to achieve best performance. Otherwise, you have more overhead. Okay? So beyond that, you have good speed up. Otherwise, you have performance degradation. Okay, the final thread scheduling approach is called dynamic scheduling. For some applications, it's possible to provide language and system tools that permit the number of threads in the process to be altered dynamically. So by using these thread tools, you can change the number of threads dynamically. So for application, you can increase or decrease the number of threads. For that environment, this would allow operating system to adjust the load to improve CPU utilization. For this dynamic scheduling, operating system and application are both of them are involved in making scheduling decisions. So scheduling is done in this way. When a job requests one or more processors, if there are idle processors, then assign one of these idle processors to this job, okay, to satisfy its request. If there are no idle processors, then if this job is a new arrival, new job, then you take one processor away from an existing job that has more than one processor and allocate this processor to this new job. Okay? To this new job. If any of the requests cannot be satisfied, it remains outstanding until either a processor becomes available. So this is simple scenario doing dynamic scheduling. If you can change the number of threads dynamically, whenever a new job is coming, if there are idle processors, you can assign them to satisfy the request. If there is no idle processor, you can take one processor from any job that has more than one processor, and then give this processor to this job. If this cannot be satisfied, if any of these requests cannot be satisfied, then this request should remain outstanding until a processor becomes available. Upon release of one or more processors, you can scan the current queue of unsatisfied requests and assign a single processor to each job in the list. Okay? So you can dynamically control the number of threads and also the scheduling. And this approach, dynamic scheduling is superior to gang scheduling or dedicated process assignment for application. They can take advantage of this dynamic thread changes, but the overhead may negate the performance advantage. Okay, so we can use this kind of approach also. So these are approaches taken by thread scheduling. So we have reviewed load sharing, gang scheduling, dedicated process assignment, and dynamic scheduling. Okay? Complex, right? Okay. So these are the issues. Let's look at real-time systems. Real-time system. So chapter 9 gives you enough details for scheduling. I think chapter 10 is an extra materials for multiprocessors and real-time systems. Okay, stack top. What are the examples of real-time systems other than this? Can you make an example? Let me ask him first. So real-time system means it's also a computer system, right? You should respond to events, external events in real time. Real time. What are the examples? Car? Yes, automobiles. Yeah, right now nowadays the automobiles have a few hundred processors, small processors, and they should respond to events at real time, right? So that's one example. Okay, how about you?
When you choose the seat on an airplane, that normally tends to be a real-time system, so that everybody can, so there are no conflicts.
A seat?
Yeah.
Seat.
When you try and check into a flight, you have to choose your seat.
That's right.
If you're in the,
A reservation system.
Yeah.
That's what you're saying. Okay. So maybe seat assignment reservation is a real time. Okay.
Audio applications.
Audio application. So maybe MP3 players.
At the moment I'm working on an effect pedal for guitars.
Guitars.
Yeah, and therefore I need low latency and
Low latency.
I need a real-time operating system.
Electric guitar.
Yeah.
Okay. I see. Stack top. How about you? Any other example? Digital clock. Do you need a computer for digital clock? Can you make another example? TV? Digital TV. Why is real time? Why is it real time?
It operates at any time. It operates at any time.
If some system is operating anytime, then it's real time. So nowadays digital TV should be interactive, right? You should respond to maybe remote in real time. Sometimes it has some on-demand video streaming coming in that can be controlled by the user in real time, right? And you can run also applications. Smart TVs are about same as smartphones in terms of its programming capability. Okay. Any other example of real-time systems? How about you?
Weather forecast system.
weather forecast system. Okay, weather forecast. How it's done?
Weather is always changing. So
Actually, weather forecast is done by the weather simulation, which actually requires some big computation time. So they are usually utilizing supercomputers for simulations, I guess. But that's also real time because the input is changing all the time. What other examples? You have other examples?
Yeah.
Okay. What other?
Amazon, eBay.
eBay?
Yeah.
eBay.
All the transactions.
All the online transactions.
Yeah.
Okay.
It's gotta be real time.
Real time. So many of the computer systems are real time. They require a real time response. In this system, the correctness of the system depends not only on the logical result of the computation, but also on the time at which the results are produced. If the results are produced too late, then there can be a problem. There can be a problem.
Would games count as real-time systems? Video games? Where you have to connect to the server and that can still count as a real-time system, right?
Maybe soft real times, right?
Yeah.
If you classify them. Okay. And real-time tasks attempt to control or react to events that place in the outside world. Because these events occur in real time, task must be able to keep up with the event in time. Okay, and we can classify real-time task into hard real-time task and soft real-time task. Hard real-time task means it must meet its deadline. The deadline is very hard. If you miss, then it will cause unacceptable damage or fatal error to the system. It's called hard real-time task. Soft real-time task means it has an associated deadline which is desirable but not mandatory. It still makes sense to schedule and complete the task even if it has passed its deadline. Sometimes they can tolerate the delay, right? So maybe the TV, whenever you watch TV, sometimes there might be some delay, but you can tolerate video stream a little bit, right? Even though it's online real-time broadcasting, okay? But sometimes hard real-time tasks such as maybe volcano monitoring or earthquake monitoring system or 원자력을 뭐라 그러다? nuclear power plant. So if they can meet the deadline, they can cause fatal error and can cause damage to the system or maybe loss of life is possible. And real-time task can be also classified into periodic task and aperiodic task. Aperiodic task means non-periodic task. Aperiodic task means it has a deadline by which it must finish or start. So the deadline can be start time or finish time. So some application you have to guarantee the start time. Some application you have to guarantee the deadline. Finish time, okay? And in some situation, you have constraint on both start time and finish time. You have to satisfy both start time and finish time.
Is this like bank vaults that they have to open at a certain time and they have to close at a certain time, no matter what? Is it sort of kind of like that?
Right, you have a task, right? Deadline, there are two deadlines. One is start time or the finish time, right?
Yes.
Or both, okay? And this is called a periodic task. A periodic task means sometimes for this kind of periodic real-time task has a requirement that can be stated as once every period t, they should do something, right? Or exactly t time units apart, they have to produce something or something like that. Then these are called periodic real-time task. Okay, so we can classify into two dimensions: hard real-time, soft real-time, periodic versus aperiodic task. And let's look at the characteristics of real-time systems. Real-time operating systems have requirements in 5 general areas. determinism, responsiveness, user control, reliability, and phase after operation. Let's look at each characteristic. Determinism means it's concerned with how long an operating system delays before acknowledging an interrupt. Interrupt means, so real-time system should react to events in real time, right? Outside the event. Outside the event is coming to the system as an interrupt. Okay? How fast this system can process this interrupt. So when multiple processes are competing for resource and process time, no system will be fully deterministic. So one useful measure of ability of operating system to function deterministically is the maximum delay from the arrival of high priority interrupt to when the service begins. Okay. So determinism is, as I said, the real-time system should react to events in real time, and these events are external events. So they generate this event through the interrupt pin. Okay, so there is an interrupt coming in, and how the system responds to this event is an issue. So how to handle this interrupt. There are two issues. One is called determinism, and the other is called responsiveness. Determinism is concerned about the delay from when this interrupt arrives to the time when this interrupt is acknowledged. Okay, and they should be deterministic, and they should be small. That's what this slide is trying to tell. Okay, but when multiple processes are competing for resource and process time, no system can be fully deterministic. Deterministic means it's not easy to guarantee this delay because there are multiple processes competing for resource and process time. And determinism, one measure to measure this determinism is to measuring this delay from the arrival of interrupt to when the service begins, before the right just before the service begins. Okay, so this so if you have an interrupt, so outside the event, okay. Let's assume that this is a passenger, not a passenger. Maybe in an automobile there is some outside person crossing the road, and this can cause this alarm to the automobile system because it's a real-time system. So there is an event occurring. It should generate some interrupt. So this is the time of interrupt arrival. Okay, and then this is the delay. Interrupt is acknowledged. So this delay, and then after acknowledgement, you have to solve interrupt service routine. You have to handle this interrupt. Okay, and this delay is called this determinism. And this delay is concerned with responsiveness. Okay, in this. So here it says the delay from the arrival of interrupt to when the service begins. So right before the service begins. So this is the what determinism is concerned about. Okay. You okay?
Yeah.
Your face becomes
Red.
Red. Right.
Yeah.
Okay. And this delay, so the extent to which an operating system can deterministically satisfy requests depends on the speed with which it can respond to interrupt. How fast it can respond to this interrupt. In non-real-time operating system, this delay might be in the range of 10 to hundreds of milliseconds. it takes a while to service this interrupt. In real-time operating system, this delay may have an upper bound from a few microseconds to a millisecond. So in real-time system, this delay should be small and should be deterministic. That's what this slide is trying to say. Okay, that's one characteristic of a real-time system. And the other factor that affects this delay is whether the system has sufficient capacity to handle all requests within the required time. This means whether the system has enough performance and enough resource to handle this request in this fast way. And that's the determinism. So delay from interrupt arrival to time when this interrupt is acknowledged, right before this service begins. Okay? That's what this determinism is concerned. Okay? The second factor is responsiveness. So determinism is concerned how long an operating system delays before acknowledging an interrupt, while responsiveness is concerned with how long it takes an operating system to service the interrupt after acknowledgement. So this is the delay concerned about this responsiveness. And to handle this interrupt, sometimes the amount of time required to initially handle the interrupt and begin execution of ISR. So before you handle this handle the interrupt, sometimes you have to do context switching, right? So this includes context switching time. And so maybe in a multi-threaded processor, as I mentioned, nowadays commercial processors can be multi-threaded with SMT, simultaneous multi-threading. There are multiple register files. Then the context switch time can be reduced. In that case, you can reduce this delay also, right? But if it's not multi-threaded processor, then this might include this context switching delay and actual time required to perform interrupt service routine, okay, to handle this event. And if you allow interrupt nesting, this can be also delayed. Interrupt nesting means you are servicing this interrupt. While servicing the interrupt, there might be another interrupt coming in. It's nested interrupt. If there is a higher priority interrupt, if you allow, then it will delay the response time, okay, responsiveness. So these factors can affect this response time. So context switching, actual handling of interrupt service routine, processing of interrupt service routine, and interrupt nesting. If you allow another interrupt while we are servicing another interrupt, then it may delay this delay. And determinism and responsiveness, both of them make up the response time to external events, right? Because determinism is concerned about this delay and responsiveness is concerned about this delay, and total, this is the actual delay before this event is handled, okay? And it's critical for real-time system that must meet timing requirements imposed by individual device or data flow external to the system. So external events can be coming from data flows like reservation system, as he mentioned, or it can be by individual person, right? So smartphones, you can react to the individual users, or it can come from the device, other device, okay? So you can understand what is determinism and what is responsiveness, okay? 어려워요? 오케이. 나머지는 다음 시간에 합시다. 오케이.